If my plus signs are both at the dot or both not at the dot, then there's a positive relationship here. All right, so in this case, that means there's a negative relationship. So that means that V1, if I remove the absolute values there, V1, V2, there's a negative in that case. All right, and then when I want to figure out the current relationship, basically what I do is I say if I1 is going this way and I2 is going this way, what I do is that power relationship, right? So power V1 I1 plus V2 I2 equals 0. So what I got to do is I got to figure out if this is true, if both of the currents are going into the plus sign. So that's true over here, right? Current's going into the plus sign. Other side, it's coming out of the plus sign as I've drawn this. Now, I don't know if that's the way the problem's set up, right? But that's going to put that in there. That's going to put a minus sign in there. That's all it takes, all right, to do that problem. Okay. All right, so we'll have more to say about transformers. We'll talk more about them next week. All right, no transformers on the test. All right, but you will need that to finish the homework. All right, so now we're going to jump into our last, and transformers relates to our last segment of the class. All right, which is power. Okay, and we're going to deal. We'll probably touch very briefly at the end on three-phase power. We'll talk primarily about single-phase power. All right. And to do this, I have to introduce a concept called RMS, or root mean squared. So let me go. All right. So when I talk about root mean squared quantities versus peak quantities, this is important when I talk about power. Okay. We introduced this concept. The book, and most books have a whole section or a couple of sections dedicated to trying to calculate the RMS values of different weird waveforms. We're not going to do that, okay? RMS is a typical measurement. So if you guys ever used a voltmeter, you go get a fluke voltmeter or something like that, you've ever used that, or if you go in the lab here and you have a voltmeter, if you try to measure an AC voltage, it tells you a quote unquote AC value or an RMS value. So the AC value is often what we call the root mean squared, okay? So this gets into a tricky question. If I compare a DC waveform versus an AC waveform, okay? DC waveform, there's no question about what number you're talking about if you have a DC waveform, because it's only one number, right? If I have this example here, 240 volts, 240 is the only number I could ever use to characterize that thing. But if you think about an AC waveform like this, right? As this guy goes through one period, he actually takes on infinitely many different values as he goes through that period, right? And so we started out very naturally saying, well, if I'm referring to a particular voltage, you guys created a phasor, and so the phasor for this guy would be, I don't know, if this peak value here was 10, right? What would you call the phasor for this thing that I've drawn right here? For this particular waveform, what would be its phasor?
10 angle negative 90.
10 angle negative 90, because this guy's sine and not cosine. Okay, so we had those two numbers that we used to represent it in steady state, right? Well, you know, the peak is where we started, the peak of the amplitude, right? But there's actually a lot of different numbers, and as it turns out, the RMS number, which is something we can derive from that sine wave, is actually the one that we use because it makes our power equations get very simple. All right, not simple per se. They're not hard anyway, but it makes them look better. All right, it takes some factors out of our power equations. We're going to see more about that as we go through this, but I want to first introduce this concept of RMS because, quite honestly, it is. If you go and talk to an engineer at Duke and they say, "Well, this is 120 volts right here," they're referring to a sine wave, but they're not referring to a sine wave that has 120 volt peak amplitude. They're referring to a waveform that has 169 volt amplitude, okay? Which I'll explain that relationship in a minute, right? But you've probably heard, right, at a wall socket, you have 120 volts, right? Probably heard that before. That's an RMS number. It's not a peak number, okay? So we define a couple of different values for these waveforms, okay, for AC waveforms. And just to be clear, because oftentimes when you go in the lab and you make measurements, they talk about a couple of different numbers. V peak is the amplitude here. All right. V peak to peak is from the top to the bottom, from the positive peak to the negative peak. And then there is another value, which is what we call the RMS value. All right. Now, there's a definition for RMS, but if I'm talking about the special condition of a sine wave, the RMS value is always 0.707 times the peak value. All right. And in my notes, I've got a derivation of that. I don't want to bother deriving it here, right? But it is an important result that we use often. All right, so in this case, looking at this waveform, I haven't said what A is, but A is the amplitude of this waveform, right? So here's my waveform. A is its amplitude. V peak is the peak value. So what would that be? Well, that would be A, right? What would the peak to peak value be? 2A. Right? Yeah, 2A. And what's the RMS value here? Well, that would be
1 over root 2A.
Yes, so 0.707A, which Stephen's being more exact there. It's A over square root of 2, all right, which is basically 0.707 is 1 over square root of 2. It's actually 0.707 and a bunch of other trailing numbers, right? Those definitions are really important. The one that we use, any real engineer speaks to you in RMS terms. All right, I don't introduce that when I introduce phasors, as it's not important at that point in time, and it's just another thing to confuse you guys. All right, but the RMS thing we're going to use basically from this point of the semester onward, or let me specifically say, when you walk out of exam 4 onward. All right, don't put RMS numbers on your test, and that does not apply to exam 4. All right, exam 5, it sure will. All right, so. All right, there's the derivation of it. Basically, the root mean squared. I don't want to get into it. You can look at this, but this term root mean squared, right? I just want to remember though, if I say I want to get the average value of something, how do I get the average value? If I have an x of t, and I want to get the average value of x of t, how do you get the average value of
Sum divided by a total number.
The sum divided by the total number, which yeah, as Tone is saying here in the room, is basically the integral over a period, right? That's the summation. And then you divide by the total time that's encompassed there, right? This is the average value of x. So the reason we call this the root mean squared is because, well, you take the waveform squared, you take the mean of that, and you take the square root of it, the root mean squared. It's used all the time, all right? And it is the number that engineers pretty much always refer to. So I put in cosine here, and you can see if I put in V specifically, if I put in x of t equal to V cosine omega t, and it doesn't matter. If I phase shift it, I'm going to get the same answer, all right? If I put in V cosine omega t plus phi, in fact, I did, didn't I? All right, if I put in V cosine omega t plus phi, it would still work out to be the peak value with the amplitude divided by the square root of 2. Now, what will cause on exam 5, what will cause half of you to lose credit is there will be some problem where you will write, if I had a 10 volt peak waveform, some of you guys are going to write 10 volts RMS times cosine omega t. All right, that is not correct, and I will take off points for that. The RMS value is not the amplitude. The RMS value is 70% of that. All right, that's an argument I've had many times with people. Okay, all right, so the peak value is the amplitude of the waveform. When you write the time domain expression, you don't write the RMS number times cosine. You write the peak value, the amplitude times cosine. All right, now again, at this point in the delivery of this, it's like, well, why is he talking about this? Well, it does matter when we talk. 2 reasons. Engineers always use it. Second reason, it is fundamentally what we use anytime we're talking about power. Okay, so talking about just trying to get a sense of what I'm referring to here, this is an oscilloscope measurement that I took at a wall outlet in this building. Okay. So a couple of things about that. Is that a sine or a cosine wave? Would you call that a sine or a cosine wave?
Wouldn't it be like inverted sine?
Well, so
kinda weird.
this isn't a trick. This isn't a math. You guys are used to math questions. Like, it's not. I'm not asking like, give me the trig function to it. Does this look like a sine or a cosine should look?
Yes.
Yeah.
Okay, it does kind of. The one thing I would say about it is a little bit flat topped. A true sine wave should be a little bit more round than this guy is. All right, that's pretty common. All right, and that's because there's distortions that are happening in that system, in the power system. In particular, it tends to happen near the peak. It tends to get kind of flat topped a little bit. So when I look at this, a couple of things that I wrote out to them. And the reason I just point that out because what you will see is the waveforms will get distorted and dirty out there. Not too distorted, but they will get distorted a little bit, meaning they'll flat top a little bit. All right. So when I look at, I got a couple of things that I put here. I got three sets of measurements. So what I see is I wrote the RMS value. So in this case, it says 122.56. In this case, this guy was 122. Right, and it says his peak value is 165.8. I'm going to round that up to 166 volts. If you do the math on that, that's pretty close to 166 divided by the square root of 2. If you do the math, it's not quite that. And the reason it's not quite that is because that's not quite a sine wave. All right, it is a little bit distorted. All right, and so there's some other stuff going on there. What's the frequency of this guy based on this measurement? You can see it over here, right? Well, so it's I wrote it over here, 59.985. So it should be about 60 hertz. Now you see that it's not quite, and that happens. The frequency drifts around a little bit, but it's pretty close to that. All right, but it's helpful to see that because the number we talk about. So Duke has a statutory requirement to keep the voltage within a particular level, right? They don't have to keep it at 120. All right. In fact, you go look at appliances. Sometimes you'll hear people say things are at 110 volts or something like that. Nothing's at 110. It's usually the grid is about 120 plus or minus. I don't know what the requirement is, plus or minus about 10 volts around that. Okay. So you'll see it move around, but in general, it's about 120 or so. All right. Now, it's useful to then probably put this in context of what happens at your house. Okay. So I looked at how your house was wired up. I'd see something like what I have here, right? So your house actually gets 2 voltages, all right? You may have noticed this. You go in your breaker cabinet, if you've ever done that, you'll see that you have 2 types of breakers, right? You have what we call a single pole breaker, and then you got what you call 2-pole breakers. And the 2-pole breakers basically are across 2 circuits, okay? So each breaker basically there'd be breakers on each of these places, right? Which basically are like switches, right? So I have some set of loads in my house that are fed from 120 volt RMS waveform. And then I get another guy that's at 120 with 180 degree shift. Okay. Now, if we think about what that's going to look like here, right? So basically, this would be one of those voltages, right? This would be the other voltage here, right? They're 180 degree shift. So if 180 degree shift means what? It means flip over the axis, right? So what I can do is I can say, if I look at those two like I have right here, if I do 120 minus 120 with 180 degree shift, right? So if I take the difference between here and here, what's that going to look like? So if I take the difference between this voltage and this voltage, if this guy is at 120 and this is at minus 120, it's going to what?
The amplitude is double.
The amplitude's double. I get 240 volts. Okay. So in your house, you got 2 types of loads, right? You got 120 loads. That's the stuff you're used to. All right. And then you have 240 loads. All right. The 240 loads are what? Well, like your air conditioner, right? Your air conditioner requires 240 volts.
So is that like the peak to peak value? Because the peak to peak was 2 times 8.
Well, so it's the RMS value. So what I've written here is I've written my phasor here in RMS. So it's saying that this guy is, so each phase is 120. Phase to phase, if I look at both of them, it's 240. All right. So that's not the peak to peak value. What it says is that the RMS value is 120. The RMS value of this is 240. So the peak value of the combination of them would be 240 times square root of 2. All right. So it's a lot bigger. All right. And so we typically put loads that need a lot of power on the 240. Right? Because we don't, if we put them on the 120, it would be a lot of current to give the same amount of power. Okay. So there's very few stuff that's there, right? So one of them would be the air conditioner, like I got drawn here. What else gets the 240? Fridge does not.
Dryers.
Dryers are the big one. Washing machine typically not. Right? The dryer typically does, because the dryer's got a lot. Where's the power going in the dryer?
Motor that spins the giant
Not
Heating coil.
Not to the motor. Yeah, that was a setup. Not to the motor. It goes to the heating coil. Heating coil needs a lot of power, and it heats up that stuff. The motor doesn't. So like, for instance, in a washing machine, it usually doesn't have 240, because it's the motor in there doesn't take a whole lot. Motors don't usually require as much as, at least at home, motors don't require as much as the heating elements do. Okay, so we can talk about that kind of stuff for a while, but so a couple of terms that I think it's useful for people to know too when you're thinking about this stuff is I use these terms hot and neutral, right? So basically the hot is basically the plus, and the neutral is the minus. If you open up a wall outlet, you'll see the hot is always the black wire, and the neutral is the white. Okay, and the neutral is grounded. Okay, so we can talk about that for a while. So there's a picture here you can look at in the notes about how that relates to what's actually in the wall, the blades on the wall socket, right? If you want to see that, all right. And some of you guys, if you've done internships and things like that, you've probably heard 120, 208. You probably heard 480, 277, things like that. So there's different voltages throughout the network that are common. Okay. All right, but those numbers are always RMS numbers. All right, so I want to unify us with the RMS. I'm not going to ask you guys to start computing RMS of weird waveforms. We're going to focus on sine waves. All right, we're just going to say that the RMS value is 120 over square root, sorry, peak value divided by square root of 2. For safety. For safety. So that's a separate, I talk about that after class if you want to know more about that. It's a safety thing, but you always have 3 prongs in the plug. The third one should have no current, but is there for safety. And this is real world stuff, so people have all kinds of questions.
But before we continue, what's like the main takeaway from the voltages we've been calculating and working on versus the RMS voltages?
Nothing. It's just like if I gave you, it's a great question. So what Eli asks is, what's the difference between what we've been doing up until now? We've been doing everything in peak values. All right. And that just means that, like, if let's say you took a homework problem where you got that the voltage across some capacitor was 12 volts with an angle of 30 degrees, that means that's the amplitude of the sine wave that would be measured there. But the RMS value would be that divided by square root of 2. That's the only difference. All right. No difference other than that. All right, you can do your phasors. So actually I wrote that here, right? So these are my phasors in RMS. These are my phasors in peak. There's just a square root of 2 multiplying everything when I do that. Okay, doesn't change anything about our process. So what I want to do is we use that to talk about single phase power. All right, I'm going to talk specifically about single phase power. I differentiate that between what we call 3-phase power. Single phase is what you have at your house. All right, 3-phase is what we have out there on the power grid. We're not going to talk about that so much right now. We talk about single phase power. Now, power, what is power?
Voltage times current.
I wanted you to say that. That's not quite right. It's, well, what's the definition of power? Anybody remember? Truly, I mean, it is V times I.
Is it energy used per second?
Yes. Yeah. Tone and Musa both got that here. So yes, it is energy used per second is the definition of power. All right. So what that means is it is oftentimes energy is W, right? We're not going to talk about energy a whole lot here, but I'm going to say energy is often written as W because energy and work are the same thing, if you remember your days in physics. So power is the partial derivative of energy. That is its definition, okay? Now, the reason I say that is, this was a pretty minimal thing to think about in the context of what you guys learned when you learned power in DC circuits, because there wasn't any time variation. DC circuits, right? I turned on a 5-volt source and power went through, right? There was a current. AC stuff's a little bit different, all right? Because we have varying waveforms and stuff. And we have elements that do what? Right? So we talk about AC circuits. You guys first learned power. The only thing you had was resistors, right? What do resistors do? They absorb energy, right? So energy is going to a resistor and it's being converted into some other form, heat probably, right? But in the case of a capacitor or an inductor, what's going on? Capacitors, inductors store energy, right? So if I want to say, now I can derive that this is related to V and I, right? So if I go back, boy, I don't necessarily need to do this here, right? But energy is V time. If I look at a particular charge, a charge has a particular voltage. Energy per unit charge is voltage, right? So if I can do this guy out to be, I don't need to do it. What's the rate of flow of charge? It's current, right? So basically I derive from the true definition of power, right, that it becomes V times I, right? Now, I don't need to worry about this too much, but we'll get back to that because power has sort of a different meaning. Now, one of the reasons I did this is I said P of T. What does that mean if I say P of T?
The rate of power with respect to time.
Well, it means that it's potentially changing over time. It's not always the same number, right? So that's important. Now, you guys learned with the passive sign convention in circuits 1 that if I have a particular voltage, all right, across a load, and I have an I of T going into that load, right? If power is positive, then that unit is absorbing energy, right? So if I'm talking about a resistor, what should power always be? Power should always be positive. If I have a source, power should always be what? Negative. All right. So power leaves a source, power enters a resistor. What if I have a capacitor? Could go either way, right? So that's an interesting question. It could absorb it or it could source it because it stores it, right? So we got to figure out a little bit more about this whole story. So let's talk about this circuit here. So let's say I take a light bulb and I hook it up to a 120 volt source. All right. If I did that, took this light bulb and hooked it up to a 120 volt source, and it was a DC source, you could do that. Light bulb would be okay with getting 120 volts DC. And the power is 100 watts. All right. So if I was doing that, I wanted to figure out what's the current going into that thing.
100 divided by 120.
Yeah, so you guys remember power for a resistive load, power is equal to V times I, and it's equal to what? So if I'm talking resistive loads here for a second, resistive loads, DC circuits, I squared times R, and what's the other one? Somebody online?
V squared over R.
V squared over R. Those are our three basic power relationships for DC circuits, okay? So if I want to get the current, like Gideon said, yeah, basically I'd say the current would basically be the power divided by V, all right? So if I had 100 watts and 120 volts, that would work out to be about 0.833 amps like that, okay? Now, in that case, what I want to ask myself is, what would that look like? So say the power is 100 watts. What does that mean? What does it mean that the power is 100 watts?
It means it's dissipating 100 joules per second, is it?
Yeah, it's the rate at which that guy is converting electric energy to some other form. Some of it light, some of it heat. All right, so it's 100 at 100 joules per second. That's the rate at which he is converting electric energy into some useful form. I use the term useful form, light or heat. The light's really the only useful part, but it's converting it to some other form. All right. So if I drew P of t, right, at time t equal to 0, I applied a voltage of 120 volts to this thing. What would P of t look like?
At 0?
Yeah. So at time t equal to 0, I had a switch and I turned it on. Right. This guy's all resistors. So what would the power look like over time?
It's going to increase exponentially and then just plateau, right?
It would just be constant, right? There's no inductors, nothing in this circuit, nothing fancy. This guy is a resistor. I mean, I should be clear about that. He's just a R, right? A light bulb is, if you opened up a light bulb, there's just, basically it's a resistor between those two leads, okay? So it would be a constant. It wouldn't change. There's one number, 100 volts, 100 watts, okay? Now, what if I instead hook that guy up to 120 volts RMS, okay? And so if I said 120 volts RMS, what is the actual V of t in that case? So if it's 120 volts RMS, how would I write that? 120 times the square root of 2 would be its actual peak value, right? Times cosine. And in this case, I gave you a frequency. I said cosine 2 pi 60t.
So we can't write the phasor just with the RMS.
You can write the phasor with the RMS. I'm writing the time domain waveform here,
Okay.
right? So I'm saying the peak value of that guy is 120 times square root of 2, which works out to be 169 volts. So the peak, so V peak over square root of 2 is equal to VRMS, right?
And you were saying earlier that what students make a mistake of is they just put the 120 cosine 2 pi 60t.
Yeah.
Okay.
Yeah. So it's always the peak value, because if you think about it, right, it's the maximum value of cosine is 1. So the maximum value cosine is going to take is 1 times whatever the amplitude is. Okay. So yeah, you make sure to get that peak value right. This question always finds its way out of the test because it always catches a lot of people. Okay. All right. So if I said in this case, what's my I of t in this particular case, right? What would my I of t look like? Well, I gotta say this guy's a resistor, right? So this guy's got a value R, right? So if you were going to solve this problem, right? I gave you this problem, and you would do phasors on this, and you would say, well, the phasor for this guy would be 169, right? If I'm using peak values like you always have, you would say this guy has a phasor that is 169 angle 0, right? And I ask you to solve for the current. This, if I did the math for a 100-watt light bulb, suffice it to say it's about 144 ohms. All right, just take my word for that. All right, you can't even buy a 100-watt light bulb anymore. All right, I guess. All right, maybe Trump made them legal again. I don't remember, but Biden probably unlegaled them, I guess. That would be my phasor, right? So if I look at that, so what would this work out to be? If I did this math right here, this guy would work out to be, I don't even care what the answer is, right? I think it's about it's about a little bit more than 1 amp, right? So if I said, well, what's that current look like in time, what would it look like in time? Would it be shifted? What's that? No shift. Why is there no shift between the voltage and the current here? Because there's what?
There's a resistor.
Just a
and then
resistor.
phase angle.
With just a resistor, there's no phase shifting, right? Resistors, everything stays in phase. So this guy would be, I don't know, whatever that works out to be, V peak over R cosine omega t. Okay. All right. And the voltage, V of t, was V peak cosine omega t. All right. So the power is V times I. Okay. What is that? What would be the expression there? So I of t is this guy, right? I of t is some cosine. V of t is some cosine. What would I write for V of t times I of t? It's what? Yeah, so I'm gonna have V peak over R. This is my I of t, cosine omega t. And I'd have V peak cosine omega t, like that. That would basically be V peak squared over R times cosine squared. What would that look like? Anybody know? Well, it would look like that, right? If I take cosine squared, you go do some trig identities, and we're not going to do a lot of trig identities here, so don't worry, right? What I see is, I took a light bulb and I looked at what's the voltage and what's the current, right? First thing I see about the voltage and the current is, in this particular case, if I look over one period, so those red bars there delineate one period, right? So when I look at a period, first thing is the voltage and current are in phase, right? How can you look at that and know that they're in phase? What's the reason you know they're in phase?
Peak values are the same or in line.
Yeah, peak values line up with each other. Now the power, what would you say about the power? What would you say about the frequency of the power relative to the voltage?
Double.
What's that?
Twice the frequency.
Yeah, it's twice. Yeah, doubled. Yeah, I think that's what you said, Steve. It's doubled, right?
Yeah.
So it's twice that value, or it's twice that frequency. All right. Now the other thing that's maybe important to me is when I look at this particular thing right here, right? What's all of our AC waveforms have no average value. Okay, so notice like my voltage here, it starts at negative 169, goes up to 169, and just moves around zero. What do you notice about this axis here? Maybe I
It's
covered
all
it up.
positive.
It's all positive. The fact that power is always positive, what did we say that meant back at the very beginning earlier?
Absorbing energy.
It's absorbing energy. Light bulb does nothing but absorb energy, right? It's just basically, it's like my kids. It does nothing useful. It just consumes from me, right? So basically, the whole idea here is this guy is always absorbing energy.
So does the generation of energy measured in negative power?
Generation of energy is negative power, right? A source gives you negative power, right? So I'm generating 100 watts and absorbing 100 watts. So usually when something's generating, it's written as a negative. Okay. All right. So the thing is, though, this is not fun in the same way that so when we had DC circuits here, right? You said, 120 volts, 100 watt, it's 100 watts, right? One number, right? This guy's a 100 watt light bulb, isn't he? Right? Where's the 100 watts here? Well, it's one of the numbers that's, this guy takes infinitely many values between 0 and 200. Okay. So if I look at this guy looks like, to me, if these guys were, sort of cosine omega t, these guys down here look like they're cosine 2 omega t, don't they? Right? Plus he has some kind of an offset. What do I mean when I say offset?
Shifted.
It's shifted up, right? So somehow it looks like that. And if I did the trig identity to unfold this thing here, right, this cosine squared term, that's exactly what would come out, is a constant plus a cosine 2 omega t, if I did my trig identity. All right. Thing is, we're talking about 100-watt light bulb here, so we don't, so electricians don't talk about cosine squared very often, right? So what are we talking about, do you think? Where do you see 100 here? In the middle. And what's that look like? What would you call the middle value here? It's the average. Over that period, that's the average, right? So what we talk about is, if I go through that expansion, right? In fact, this is what I get if I go through that expansion, right? What I see is V peak I peak over 2 plus V peak I peak over 2 times cosine 2 omega t. All right. What's the average of any cosine as I go through one period? What's the average of cosine or sine?
0.
So it's always 0, right? So if I take the average of this, so if I said, let's take the average value of P of t, right? Take the average value of that. That's taken, so I write these little brackets as one way sometimes of defining power, and when you're talking about waveforms, right? If I talk about that, I don't want to write that whole expression again, but if I say this whole guy here, if I shifted that down and said, take the average of that, what is the average of that? So if I gave you this, so V peak, I peak over 2, those are constant numbers. I can figure those out from solving Ohm's law in the circuit, okay? The average value is just going to be V peak, I peak over 2, all right? So if I go in and I do that in this particular case, right? I do 169 as the peak voltage, right? I think my peak current actually works out to be, if you look at the picture, it's like 1.1 something like that. It's like 1.17 or something like that. All right. And divide by 2, you work out that's about 100 watts, right? So what we talk about, if I'm talking about this, so what I added, I took my picture there and I modified it. What I did was I basically had something go along and calculate the average value. Okay. So the average value of this is 100 watts. Okay. So what we talk about AC systems is we bring in that definition of the average. And we talk about doing the average over a single period of that power. And in this case, it's 100 watts. All right. In general, right, it's going to have a particular, it's going to have a relationship to it. All right. There's going to be a formula for it. Sometimes people get bogged down in power because there's a lot of formulas. All right. Monday next week, when we start talking about this some more, I will give you in my notes a summary sheet of all of the formulas that, that you'll work from. All right. Because you can get bogged down in it. The important thing is we talk about this. I often say the average power. Okay. You'll hear engineers use a couple of different terms. Real power or active power sometimes is the term that they will use. But basically, it's the average power. So we'll define this here. I have it in the notes. P of t is instantaneous power. Instantaneous power. Okay. The power at any instant. Right. So if I look at this light bulb, right, at some instant, the power is 200 watts. Some other instant, it's 0 watts. But on average, it's 100 watts. And that's the number. So we use the real power, active power, average power. Those all mean the same thing. All right. What it is it's the average of that instantaneous power. So it's the average rate at which energy is being converted in that thing. Otherwise, we need some number to refer to, and nobody likes to think about the cosine squareds and all that kind of stuff, right? So as much as you guys think we're all about math, right? We actually try to take math out of the picture as much as we can, right? No electrician is out there talking about cosines, right? But they are talking about 100 watts. Okay. All right. So this guy is important, but what happens if I get sort of a different picture? All right. What happens if I get sort of what I call a generalized impedance, right? So instead of having a resistor, let's say what I've got is some load which has some impedance. All right. So there works out for me to be, sort of a couple of different scenarios for what I would talk about here, right? So inductor, capacitor, resistor. All right, so in general, I can talk about my impedances as having some magnitude and some angle, right? So I'm talking about an inductor. So that's what I have here in the lower left. Here's an inductor, okay? What would you say, what's the so J omega L is our impedance, right? So we've talked about that before. You guys know that, right? What's the angle and the magnitude of that guy? What would you say is the magnitude and the angle?
Magnitude is WL and the angle is 90.
So omega L angle 90, yeah. So I draw him as a phasor pointing up. Now we talked about phasor diagrams before, but now when I go into power, I'm going to use the phasor diagrams a lot. So I'm going to try to show where the phasors sit in the complex plane. So that helps us think about power, okay? So if you look at the guy at the bottom, right? So in the middle here, so Z equals 1 over J omega C. That's what I've got for, what's some short shorts, man? I was sorry, I was a little, Eli's wearing some short shorts. You guys agree with me? All right, thank you. Yeah, that was weird. All right. Fortunately, I'm recording doing that. So 1 over omega C, what's the angle on that guy? Angle is negative 90. Okay. What about for a resistor? What's the angle on that? Yeah, that guy's angle is 0 degrees. Okay. All right. So those are our basic building blocks, but most of the time our impedances are not just an inductor, just a resistor, or just a capacitor. It's a combination, right? So we're going to deal with those combinations, but I first want to think through what happens if I have an inductor, all right? Just an inductor. And I'm taking the same thing. I'm taking my voltage source and I'm hooking it up to a load, and the load's just going to be an inductor, okay? So if I did this, a couple of things that we're going to try to think through real quick, right? So I have a voltage source. This guy has an angle V. So I'm trying to keep it general. I'm saying is that he's maybe not just cosine, he's got some angle. Could be plus 30 degrees or whatever, okay? All right, so if I'm looking at this and I wanted to figure out what's the relationships that would exist in this particular case, all right? How would I figure out the phases of the current? So V equals IZ, all right? How would I figure out the phase relationship for everything? So V equals IZ. So first of all, that means that the magnitude of V equals the magnitude of I times the magnitude of Z, right? That should make sense. So if I'm talking about an inductor, that means that the magnitude of V is equal to the magnitude of I times omega L, okay? What about the angle? So it's angle of the voltage equals what?
Angle of the current
Angle of the current
plus 90.
plus 90 degrees, okay? So that means that the angle of the current is equal to 5V minus 90 degrees. All right, what does that mean? So in this case, what I do, I drew my phasor diagram here, okay? What's the angle of that phasor? I put a voltage phasor there. What's the angle for that voltage phasor? What's the angle for that voltage phasor? 0, right? So my inductor has an impedance angle of 90 degrees. That means it's pointing up, okay? So I wanted to show where the current is. So if V was at 0, I is at negative 90, correct? Right? It's 90 behind, like this in my phasor diagram. So we're gonna talk about what this means in the time domain, but this phasor picture becomes really common when we look at power. All right, because we start talking about, in this case, what would I say? I used the term at the very beginning that we're going to use a lot more. In this case, is that current leading or lagging the voltage?
Would be lag, correct?
It would be lagging. All right, its angle is behind the angle of the voltage. All right, it is a more negative angle, I guess, if you will. All right, it's 90 degrees behind. All right, I have I have a complete set of sort of summary slides that goes through leading, lagging, all that stuff with all the formulas. But when I see this guy is behind, meaning he's at a more negative angle, I had to rotate this direction to get from voltage to current. That means that he is in a lagging situation. So what's that mean about the time domain waveforms here? Well, V of t is V peak cosine omega t plus phi V. What would I say I of t looks like in this case? Well, it would be I peak. So I peak would be V peak divided by omega L. All right, be that. You watching in the bathroom or something? Wait till you watch the video later. All right. What's the angle? What's the angle of this guy? Well, the angle of this guy would be whatever the angle of I is. All right. So what would that be in terms of the voltage angle? Well, if I plug this guy in, V peak omega L cosine, we can get lost in the math. I don't want to get lost in the math here. All right. If I talk about phi I, we talked phi I is 90 degrees lagging the voltage. So I'm going to say plus phi V minus 90 degrees. Okay. What does that voltage and current look like if I were to show them? How would they relate to each other? So what you said something about sine, Christian says something. Yeah, cosine and sine. If phi V was 0, there'd be like this cosine sine relationship. There's a 90-degree shift between them. All right, so if I have a negative 90 here, which direction am I going? Somebody online?
To the right.
Yes. Okay. So there's my voltage. My voltage is cosine. My current becomes sine. All right. So they're shifted or out of phase by 90 degrees or a quarter of a period. All right. If you do it that way. What I showed at the bottom is P of t. All right. I showed the power. All right. So what I did here, P of t, right? You'd plug in, V peak cosine omega t plus phi V. You plug in I peak, right? Cosine omega t plus phi V minus 90 degrees. You do that math and you get this result here, right, that I've shown. How does that look in comparison to what I had before with the resistor? All right, so let's go back to the resistor picture. All right, so with the resistor picture, what did we say was true about it? What's the maximum and minimum of the power here? 200 and 0. So that guy has an average value that we said was 100, right? What's going on with this picture?
The average is 0.
Average is 0. No, the average is 0 for this guy. Okay. And so we got to figure out what's that mean. So to do the average, right, I basically just, say, all right, do this 1 over t average. So you compute that value. So it's pretty clear from that picture, though, without doing the math. This is fun, right? Because we can do calculus by pictures, right? So the average value of this is 0. So what does that mean? So what did it mean? So we talked about this before, right? So P of t is the rate at which energy is used, okay? And we said that's got sort of two meanings. There's the P of t greater than 0 and the P of t less than 0. So what do we say was happening when it's greater than 0? It's absorbing, right? This is absorbing. What happens, somebody online, what happens when P is less than 0?
It's acting like a power source.
It's acting like a power source, right? So this guy is storing energy here. In fact, all right, so this is storing. He's absorbing it. And then what's he doing here? He's giving it back. He's releasing it. So over a period, he doesn't use anything. All right. He takes some from Duke and then he gives it back to Duke. Right. That's basically what's going on when I have a capacitor connected to the power grid. And that works out to be a pretty useful thing in a lot of cases. All right. The thing about that is that's a little bit weird, isn't it? You didn't have that in the case of a DC power system. I need to give this some name, right? This is not average power, right? I don't have a 100-watt inductor here, do I? Right? There's no reason to kind of think of it that way. So I need kind of a different name for it. Okay. So, so basically, what I'm saying is no net energy is transferred in this case to this load, right? On net, there's no average energy transferred to it. There's an average power. There is a net energy transferred to that thing. Okay. Now, what we do, we need to give that a name though. Clearly this guy is still doing something. There is current that is moving through the power grid to provide energy to that inductor, right? There is current moving through the power grid to charge the inductor and discharge the inductor, right? Duke is having to supply current. There's current flowing out of its generator. There's coal being burned or gas or salt, photons, whatever, that are basically creating that current that will make that power be absorbed and then released. We need to give it a name, and we do, all right? We call it reactive power, all right? Or we're going to give that a name called VARs, okay? That basically it's the portion of P of T that represents the stored energy, all right, which also goes back to the source each cycle. So in reality, what's going on is every cycle of that 60 hertz, those inductors and capacitors are absorbing energy and then giving it back. They're absorbing and giving it back, all right? And they're just basically in this sort of sloshing. And we call that sloshing energy this reactive power. This guy, ultimately, a little bit later on, I'm going to call this guy Q, all right? Reactive power, or Q. And then this guy, I'm going to call P, all right? The real power is going to get the name P. Now notice it's a capital P. I'm specifically using capitals. I have this little p over here for my instantaneous power, and I'm going to use capital P's, all right, for this situation. Okay, so you can go through and you can do a similar process for a capacitor, right? Same thing's going to happen for a capacitor, all right? It wouldn't be that big of a deal to go through this. I want to look at kind of a more general situation though. Let's say I had this guy right here, all right? So I've got a voltage source V. What's the angle of this voltage here? The voltage I've drawn in that picture, what would be the angle of that voltage?
0.
0.
All right, so yeah, so if I'm writing this guy in terms of peak quantities here, which I will, my phasor, I'm going to say is that. But for this picture, 5V is equal to 0. In general, it's not, but in this picture, it's 0. My impedance here, what would my impedance be? Well, this guy looks like he has a particular magnitude, right? Z. He also looks like he has a particular angle, right? So I'll say it's angle of phi z. So that looks like he's about 30 degrees. Let me ask you, what is that? What kind of device would that be? If this guy has a positive angle, if this impedance has a positive angle.
It's an inductor?
It's an inductor in series with a resistor.
Inductor in series with a resistor, all right? It basically has to be an R and an L. That's pretty common. How do I know how to be an R and L, or how do Gideon know, and Tone and Christian, how do those guys know? Well, so J omega L and R, right? This guy has an angle of 0. This guy has an imaginary part that is positive, right? That's 90 degrees, okay? So the total is going to be something that is positive, okay? All right, so if I did by Ohm's law, if I want to figure out what the current's going to be, so I can go back to Ohm's law here. So V equals I Z. So if I did that in terms of angles, right? What's the angle relationship there? Well, it's phi V equals what?
Angle of I.
Angle of I plus the angle of Z. Okay. So notice, just like I did before, where is phi I? Where is he relative to the voltage? He's behind it. He's lagging again. All right. All right. Because essentially, if this guy is 30 degrees, if this was 30, this down here would be negative 30. Right. That's always going to happen with, I'm going to have with an inductor. The inductor the impedance is going to have a positive angle. The current is going to be behind the voltage. Okay. Current's going to lag the voltage. So we're going to deal more with those terms. We're going to do a lot of examples, all right, beginning next week. All right, but we got to get some of the basics understandings down. So if I have this scenario and I say, well, my P of T in this case would be P of T equals V of T, I of T, right? I multiply those two things out. I would get, using trig identities a couple of times, I would get this ugly relationship here, okay? So essentially what I did here was I took my V of T, I took my I of T, and I multiplied those guys out, all right? And then I used some trig identities to expand it. Okay, so help me out. Is there anything time varying in that term right there? No.
No.
Nothing depends on time. Angles don't depend on time. Amplitudes don't depend on time, right? No time dependence there, okay? These two terms do have a time dependence, right? There's a cosine 2 and there's a sine 2. We basically, so the terms here, this guy is associated with the power to resistor, or I should say specifically the current to the resistor. And this guy is associated with what I'm going to call, in general, the current to the reactance, where reactance is my general term for an L or C. All right. And I'm going to give, there's a couple of things here on these slides that are terms that I'm going to utilize that I want to give some names to here. All right. So this guy right here, let me see if I've got, yeah, I do. Okay. This guy right here, this guy's all constant. This guy I call P, right? If you take the average of this whole thing, right? These guys have time dependency. What do we say was the average value of cosine?
0.
0. The average value of this guy? 0. Okay. So this guy right here, this first term is my P term. Okay.
Little p or big?
Big P. So little p is the instantaneous power. We're not going to worry about instantaneous power very much, right? We talk about it today. There'll be 1, maybe 2 problems on the homework. But if we've got 2 or 3 homeworks left, that means you got 2 or 3 problems that are going to have P of T. All right. Most of them are going to deal with capital P here. Okay. All right. So this guy is also, he looks the exact same. We call him P. What's the difference between this term and the term that I call P? Not much of a difference, but there's a little bit of a difference. What's that? Well, this guy has cosine. What does this guy have? Sine. This guy I call, by definition, Q. So I rewrite this thing like this, right? And I make 2 definitions. Okay. The average value is P. The amplitude of this term is P. The amplitude of this term is Q. And the terms that we use, real power is by definition this. Reactive power is by definition this. So notice our power equation, if I just look at my real power equation, you're used to P equals VI, right? Not true anymore, okay? Right, what do I see? Well, it's the peak value of V times the peak value of I.
So is average power and real power the same thing?
Average power, real power, active power. Those are 3 terms that often mean the same thing. All right. If I look at this expression, this is not like my DC thing, right? because I also not, so I have V peak, I peak, I have this over 2. And I also have this cosine thing right here. All right, we're going to talk more about this. This guy has a name, cosine phi V minus phi I. He has a name. If I had a resistor, what would that be? If my load was a resistor, what's phi V minus phi I if I have a resistor?
IV.
Yeah, so phi V minus phi I would be 0, right? So if I had a resistor, right? So that cosine would become 1. Cosine of 0 is 1. We're going to give that guy a name. I'm not going to define it here today, right? But we're going to give it a name later on. All right. So I don't want to look at all of my examples here. I want to look at my examples later. All right. But I want to touch on something here for a second. Why RMS? Because I started with that. So I said, well, we're going to use RMS. Well, notice this whole thing, right? So all these guys here, if you look at this guy, this was my P term, right? That was my P term. My P term has this V peak, I peak over 2, okay? The over 2, everybody forgets, right? So if I remember the fact that RMS has this over square root of 2 term in it, like that. If I looked at that, right, if I took IRMS times VRMS, right, I just plug in that that's I peak divided by square root of 2 times V peak divided by square root of 2. What's that equal to? If I have square root of 2 times square root of 2, what is that equal to?
I peak, V peak over 2.
I peak, V peak over 2. So what that means is all these places where I have I peak, V peak over 2, I could replace that with VRMS times IRMS. So I can do V times I instead of V times I over 2, right? That's why we do it, right? So if I had a resistor, and this is maybe I don't think I don't have the table here. I have the table in my full notes, but I don't have the table here. All right, if I looked at a DC circuit, all right, let's do it this way. All right, sometimes they call these effective values. If I look at a DC circuit, right, if I have a resistor like this, 144 ohm resistor, right, and I looked at a DC circuit, and versus an AC, and I'll say do it in RMS, okay. If I looked at my V, I, and my average power, right? If I applied 120 volts, I had 144 ohms, this would be 0.833 amps, and my power would be 100 watts, okay? If I had 120 volts RMS, which would be 169 volts peak, this would be 0.833 amps RMS, and this would be 100 watts, the average power. So what happens is sometimes we call the RMS the effective DC value because it's like applying 120 volts DC, right? So the reason people use it is because it's effectively, it makes everything look exactly like it would if I had a DC waveform that had the same value. All right, and that's the primary. So 120 volt DC source and an AC source with 120 volts RMS gives me the same current in an RMS, and it gives me the same average power. All right, so sometimes they call it an effective DC value.
But what's happening behind the curtain that a value of 169 volts can give you the same current as a value of 100?
Well, the current is doing this, right? The current's always a different value. But the math is such that the numbers you get when you do the analysis are the same as if you had a DC voltage source, right? So there's no magic to it per se, other than the fact that the numbers are the same. And engineers like that. It makes the world look simpler, right? Than it really is, right? But so basically, this is where I end it here for today. So RMS values are what we typically use. You get a multimeter. You have one of those yellow fluke meters out there in the field or whatever. Basically, that's, you know, it's AC mode, you get an RMS number. Engineers almost exclusively use those, right, when they talk about AC. And we will use it for the remainder of the class following the end of exam 4. All right, so don't go into exam 4 and start worrying about RMS numbers. All right, that's not a thing. Okay, but you will see that in the next homework. So we got a lot. We got to define some stuff. We got a couple of more things to do. We're gonna look at a lot of examples, right? Of okay, well, so I've got a voltage source hooked up to some impedance. What's the P? What's the Q? What's all that stuff, right? We got a couple of things to define, and we've got some problems to do. Okay. All right, but I'm gonna stop it there for today.